Okay, so good afternoon everyone. This is the NPTEL course Experimental Physics First, so the interactive session for the Experimental Physics First course. This is the week 7th, that is the 7th interactive session, and I am Renalini, PMRF Research Scholar from School of Physics, University of Hyderabad. So this interactive sessions, as you all know, happens every Saturday, 3 to 5 p.m. and the recordings as well as the PPT material is available on the drive that has been shared with you all. So first, let's have a recap of what are the things that we discussed in last week. So last week we discussed about this experiment of determining moment of inertia of a flywheel. Before that we had also tried how to calculate moment of inertia of different shapes of different shaped bodies, and then this was the experiment on determining the moment of inertia of flywheel particularly, where moment of inertia formula, the working formula we had derived, which is as shown here. This is what we had done last week. Last week we also discussed another experiment, which was measurement of surface tension of a liquid. We had discussed about the theory of surface tension and understood the procedure of this experiment, where this shown here was the working formula for this experiment, and we finally wanted to determine the tension. Okay, so these were the experiments that we had discussed last week, and also we did several problems based on these concepts. Now this week we'll be discussing, I think, 2 or 3 experiments and their theories, and also assignments, last year assignment problems, or some more questions I have brought from other sources. Okay, so starting with this experiment, determination of coefficient of viscosity of a liquid. So first let's recall, of course all these things has been taught and you have learned it in class 11th or 12th standard, but recalling and revising these things is also important, so I'm doing that here. So viscosity is a measure of a fluid's resistance to flow or change in its shape. So fluid, we all understand, by fluid we mean it could be liquid as well as in a gaseous state of form. So viscosity is a measure of a fluid's resistance to its flow, or any way if we are trying to change its shape, so it resists that change. Viscosity refers to a material's ability to resist displacement between its layers. It is also known as viscous force. It is the force that opposes relative motion between the layers. So as we know, that if we have let's understand through this example. If I have a container and I have a stirrer here, that stirrer is in the form of a rod, and I'm stirring this rod in this liquid, which is water, and then if I have another same beaker and I'm stirring another kind of liquid, which is some sort of thick syrup, then I'll feel that the stirring is faster in the case of water, whereas it's slower in the case of syrup or some soup or something which is thick, we know. So what do we say is like this is less easier to stir here, means less viscous. It is a little difficult to stir the rod here because it's high in viscosity. So what we are trying to say is that the fluid is more resistant here. What causes this resistance between any fluid is the cohesive force again. When we were discussing about surface tension, there also we were talking about the cohesive force between the molecules of that liquid, which is because of which the surface tension happens. The same way viscosity happens because of the cohesive force between these molecules, but in the case of when a liquid is flowing, as shown in the diagram here, liquid or fluid, it can be gas also, but in gas the viscosity is very less. So usually we talk about liquids. So when a fluid slips or tends to slip on a neighboring layer in contact in a constant flowing fluid, the two layers provide tangential force to one another in order to reduce relative motion. So if you can imagine that the this is liquid and this is some container. These top and bottom is the wall of that container, and it's like cross sectional view of this whatever container or pipe, horizontal pipe this is. So it's known through experiments that when a fluid is flowing through this kind of horizontal container or tube, the particle of the fluid or liquid which is flowing at the center of the container, that has the maximum velocity, whereas as the sorry, okay, let me take my pen. Yeah. So the particle at the center have maximum velocity, whereas as we, this is the center, as we move towards the wall of the container on both sides, so the velocity reduces, and as the layer that is in just in contact with the container wall, that has the least velocity. Okay, because it's I mean it's not able to flow easily. So relative layers put force on each other, because of which there is this resistance to the flow, which we are calling viscosity. When a flow passes across the surface, the molecules in the flow that gets close to the surface stick to it. As a result, the relative velocity of fluid around the surface or near the wall of this container is almost zero. To put it in another way, the fluid molecules are just overcome at the same speed as the surface. So what we want to basically understand is that the liquid or fluid in a horizontal tube or container, it flows in form of a layer of cylinders that I'll discuss later, now little later. And these cylindrical layers have like the center one has the maximum velocity and the outermost has the least velocity. So how do we define viscosity? Like we talked about that this liquid has low viscosity, this is high viscosity, but how do we measure this thing? So measure the viscosity is calculated in terms of coefficient of viscosity. We call it coefficient of viscosity. It is a constant value for a particular liquid or particular fluid, and it depends on its nature. And later we will discuss about Poiseuille's law, from which we calculate the coefficient of viscosity. Coefficient of viscosity, we usually the symbol used for it is this Greek alphabet eta. This is usually the symbol used. So the most simplistic formula for measuring viscosity is shear stress upon shear rate, which is causing this viscosity. So keeping this formula in mind, the force of friction, sorry, when we get it like this, the viscosity is the shear stress. Stress is force per unit area. So if force I am denoting by small a and the area by capital A, then this will be the shear stress that is causing the change in shape of the fluid, or if the flow of the fluid. Shear rate is the this velocity dv by dx, this is small v actually, this is the x that is changing. So as we showed here, the velocity is changing with the distance, like at the center it is maximum, and as the x increases, so velocity is reducing. So that change in velocity is what we call it velocity gradient, this dv by dx, because the velocity throughout the liquid is not same, right? It's changing. So that change in velocity is what we are calling velocity gradient. It is the shear rate. This is how we define the force of friction. This is our coefficient of viscosity, eta. The SI unit of viscosity is Poisson, on the name of the researcher or scientist you can call. He was physiologist I think, who brought this law that again we'll discuss soon, from which we are able to calculate this coefficient of viscosity. There are other units as well. We can convert it and put it in Newton second per meter square or Pascal second, or in CGS I think it's poise. This is SI unit. In CGS unit, this is called poise. Okay, now yeah, so how the, as you must have seen in the video lecture where the professor performed this experiment, first we need to understand how we get this, what we get from Poisson's law. And the same thing, because it helps us derive our working formula for the experiment that was conducted, that was shown in the video lecture as well. So this Poisson's law is particularly for horizontal capillary tube, or you can understand capillary tube as a cylindrical tube, where the radius of the tube is very less than the length of the tube. That's, in that case you can define it as a capillary tube. We had discussed this in case of surface tension as well last week. So okay, so if we have a cylinder, I'm making it big here so that we can understand. So that's a horizontal cylindrical tube, and the liquid is flowing through this. So liquid will flow means definitely there is some pressure difference we have created here. Say if in this at like side A, I'm calling it side A, and this is side B of this capillary tube. On side A, if the pressure is, say it's high, means P plus delta P I'm showing, and on side B if the pressure is P, then the difference in pressure will be, this is high minus on the lower side, so the difference in pressure is delta P. Because of this difference in pressure, the liquid will flow from A to B direction, right? Now what will be the forces acting in this? Okay, again as I told that the molecules or the liquid at the center has the maximum velocity, but as it goes towards the wall its velocity decreases. So this is cylindrical, means that layer of liquid which has particular velocity, that will also be in form of cylinder, right? I mean, if I consider this particular cylinder, then all the particles, all the molecules of this particular liquid will have same velocity. So if we consider this particular cylinder of molecules, and say its radius is small r, and radius of this capillary tube is capital R, whereas radius of this cylinder that we have imagined here is small r. Okay, now this is some column of liquid. There is liquid inside this particular column of cylindrical column that we have considered here. Now what all the forces will be acting on this volume of liquid? So first there will be viscous force, because this is viscosity. We understood that as the liquid is flowing, or there is change in its shape, or there is flow of any kind, so it, because of the molecules all want to be together, so they kind of resist the flow, resist the motion of molecules. So here, if because of the difference in pressure the liquid is flowing, it will also experience viscous force, that is, it will experience viscosity, which in terms of force will be called viscous force. So the flow direction is from A to B, means the viscous force direction will be opposite to it, right? If viscous force, let's call this is viscous force, this direction will be opposite to it. So for this particular cylinder, if I consider, the viscous force will be acting in opposite direction. So there will be viscous force, and we know pressure is force per unit area, means force will be, since pressure is defined as force per unit area, and this particular liquid will, this force acting will be pressure times, the pressure is the difference in pressure times the area. Area will be pi r square, this area of this cylinder. Now there is one more force acting on, oh sorry, I made a mistake. This is not viscous force, this is the due to the pressure difference. This one is due to the pressure difference, this force. Okay, the viscous force is the viscous force as given by Poisson's law. This viscous force is defined like this, like we saw here in this case. It is the ratio of shear stress to shear rate. So it's basically this. From here we can derive, right? From here we can derive that force will be eta dV by dx times this area. So this expression we will use. So this was the because of the flow, the force due to this pressure difference was this much. Now the force due to viscosity acting on the liquid, that will be, it's known actually that the direction is negative, that's why there is negative sign also that comes, but anyway that will is not a problem. Experimentally these things are known. So F viscous will be minus eta dV by dr, again the velocity gradient, dV by dr. Here the dV by dx we had written there. Now that x is this radius. So dV by dr, and now what is this area? Area of the cylinder, which will be 2 pi r times the length. Okay, let's say the length of this tube is capital L. Then this will be 2 pi r times L. This is the total surface, 2 pi rl is the total surface area on which this viscous force is acting, okay, which is the total surface area of this liquid that we have considered. Now at steady flow condition, actually the professor already has done these derivation, but we are just doing a recap kind of, so we'll just having a recalling thing. So at steady state flow, at steady flow of liquid, total force on the liquid will be zero. At steady, yeah, that also happens, but what we mean by steady flow of liquid is that at any point in this capillary tube, like for example at this point, okay, at this point of some point C, the liquid passing at this point part of the tube will have same velocity, same density and same pressure. So the liquid is going on passing, but at this particular point of time, whatever liquid is passing, it will have same velocity, same pressure, and all its parameters are same. So when flow of fluid is in such a way, then it's called steady flow. So when the flow is steady, this happens when all the forces acting together are zero. That means it's flowing with a constant velocity, because we know if forces, usually in general, forces, mass and acceleration, and if I'm saying force is zero, that means acceleration is zero. Acceleration is what? Derivative of velocity, right? So if derivative of velocity is zero, means velocity is constant. So from this knowledge we can say that at steady state flow, if means force is zero, which implies velocity is constant. That means the flow is happening at constant velocity. Okay, and also since I'm saying all the forces acting on it are zero, that means this force due to viscosity plus the force due to pressure difference let's okay. So one force is due to the pressure difference here and another is due to viscosity. So all this will be zero when I'll keep these values here, and after doing some mathematics we'll find out the expression which will give us this law, which is also called the Poisson's law. So volume, this is volume, okay, this is capital V. So volume of liquid flowing per unit time in this kind of capillary tube or horizontal cylinder is given by pi, the change in pressure, radius of the tube, the capital R I'm using, right, it's the radius of the tube, divided by 8 eta, and this is the length of the cylinder. So this is the Poisson's law, and the basis is we use this expression of coefficient of viscosity to derive this, and this is also the working formula for the experiment that was done. So yeah, before we start with the questions, so in this for this particular experiment where the professor demonstrated how to measure the viscosity of liquid, we had a setup in which one end, we were creating pressure difference between these two ends of the tube. If you remember, there was a capillary tube in which the liquid was being flowed, and we were also using a mammometer to measure the pressure difference between these two ends so that we can put the value in this working formula. And there we had measured the radius of the capillary tube, we had measured the length of the capillary tube, and we wanted to measure this eta, coefficient of viscosity. For that we were flowing the liquid, measuring the delta P and measuring the volume of the liquid flowing, and then we were if you remember, we were starting our stopwatch and then seeing in how much time how much liquid we are able to collect in a beaker. So based on that, like from that experiment, we were able to get V value, T value, and the pressure difference. Other things are constant. So the eta for that liquid is the only unknown parameter. So we were able to calculate eta from this expression. Like, I don't have space, but I'll rewrite this. This is the Poisson's equation or Poisson's law, okay, which is also the working formula, Poisson's equation. And for our experiment, if I rewrite it like this, the eta, what we wanted to find out, it will be this pi r to the power 4, this is all constant, 8 L, and eta will go there, and then volume, it will be T by V, it will be T by V. Yeah, so this was the formula that we were, it's just rearranged form that we were using for our experiment. And since we should take average values, that means we should repeat an experiment several times. So every time we were changing we can, if you want, we can change the radius, these things also, but what we were doing there is our capillary tube was same, so radius and length was same. What we were changing was there is pressure also, sorry, I missed that. What we were changing there was the pressure difference between the two ends of the capillary tube we were changing. Based on that, the flow of liquid in the time, depending on the pressure difference. If the pressure difference was high, the flow rate will be high. If the pressure difference is less, the flow will be less. So depending on this, we will get several values of eta, and then we can take average. So this was the crux of the experiment, that how did we perform that. Now moving on to the problems based on this concept. Let's start with the first question. So this question is actually based on surface tension, but it was part of last year's assignment sheet, so I am solving this as well. The question is, a soap film is trapped between a frame and a wire of length 20 centimeter as shown in the diagram here. The frame is hanging in a vertical plane and a mass is hanging from it. So this is vertically, this frame is standing or hanging vertically, where the mass m is hanging from it in downward direction. Find the value of this mass in gram such that the film remains in equilibrium. So there is a film here, soap film has been given. There is a soap film here between this frame, this is that frame, and this is the wire. So there is soap film formed here and it's hanging vertically, and we have hanged a mass m. So how much should be the mass so that the soap film remains in equilibrium? Oh shit. Sorry. So that the soap film remains in equilibrium, it doesn't break. Surface tension has been given, the value is this, and acceleration due to gravity is this. So how to find out what should be the optimum, or what should be the value of mass so that the soap film remains in equilibrium. So first we need to understand, recall for surface tension. You remember surface tension is defined as force per unit length, right? That means if I want to know what is the force, that means it should be surface tension times the length on which it's acting, right? But we also remember doing several such questions, and when we also need to consider how many surface that particular film has. Like here, this is the here are the soap molecules. On one side also there is air atmosphere, other side also it's air atmosphere. So that means there are two surfaces here. So that's why for this particular problem, the correct equation of force will be 2 times the tension and the length on which it is acting. So this will be the correct formula. Now the force due to this hanging mass, that will be m times the acceleration due to gravity, which is 9.8 meter per second square. Now one side the tension force, the force due to tension is there, which is upward, and the force due to this weight of the body is there, which is downward. So this force due to tension, right, and then the force due to weight of the body, let's call it W, and in equilibrium these forces will be equal. So at equilibrium these two forces will be equal. Thus if I equate these things, I will be able to calculate the mass which has been asked in the question. L divided by G. Now substituting the values here, the tension has been given. Okay, the thing is final value I need to tell in gram. So I'll convert this value of tension into CJs. Right now it's Newton per meter, means it's SI unit. I'll convert it into CJs. So 1 Newton per meter is 10 to the power 3 dyne per centimeter. Dyne per centimeter is in CJs. Okay, 1 Newton per meter, which is SI unit, is equal to 10 to the power 3 dyne per centimeter. Dyne per centimeter. So from this I'll find out that 0.0049 Newton per meter is equal to 1000 means it will be 4.9 dyne per centimeter. Substituting this value here, 2 times 4.9. I'm converting everything into CGS unit because the final answer is also in grams, right? That means it's in CGS. So 2 times 4.9 times the length. Here is the length of the wire on which this tension is acting, which is 20 centimeter. So it's fine, it's already in centimeter, divided by the acceleration due to gravity. Okay, this is also in meter per second square. I need to change it into centimeter per second square. Okay, so wait, G is 9.8 meter per second square. I'll change it into centimeter per second square. So 1 meter is 100 centimeter. So this will be 980 centimeter per second square. Putting this value here. This, okay. Let me calculate. You guys can also calculate, and the answer should be divided by 98. So answer I'm getting is 0.2 grams, which is very less. Yeah, so this is the answer, that this should be the weight, sorry, the mass. 0.2, this is gram, this is not acceleration due to gravity, this is 0.2 gram. This should be the weight, mass of this hanging body, so that the film remains in equilibrium. So the correct answer is this. I hope that is clear. If you have any doubt, you guys can unmute and ask. Otherwise, I will proceed. The next question is, the shear stress at a point in a liquid is found to be 0.05 Newton per meter square. The velocity gradient at that point is 0.25 meter per second. Means the shear stress is force per unit area. So I mean, just like it is some shear stress, or shear stress has been given to be 0.04 Newton per meter square. Velocity gradient, we know now what it means, right? Velocity gradient, which we denote by dv by dr or dv by dx. Anything is fine. Basically, we should have clear understanding that this is the rate of change in velocity with respect to the distance. So velocity gradient at a point is, the value is 0.25 meters per second. What will be its coefficient of viscosity? So we know the formula, that coefficient of viscosity, eta, is given by the minus sign. We don't need it for calculating the magnitude, it's fine. Otherwise, just to write, it's given by this formula, right? dv by dr. So the shear stress, which is force per unit area, so I'm using that here, 0.05 Newton. We'll write final thing. dv by dr is 0.25. So the final answer will be 0.05 divided by 0.25. Answer is 0.2 again. Okay. The answer is 0.2 Newton second per meter square. So answer is A. Okay. Next question is, two plates placed horizontally separated by a gap of 0.5 centimeter, and gap is filled with an oil of coefficient of viscosity 5 poisers. So yeah, I told you, right, that Poisson is also one SI unit. We use Poisson or Newton second per meter square, you can call it, and CJS unit is one poise. CJS unit is poise. So that one, just to, we'll be using this, that's why 1 Newton second per meter square or 1 Poisson, which is the SI unit of coefficient of viscosity, is equal to, or sorry, 1 poise, which is given here. This is CJS. Just remember, this is CJS. And here the answer is in Newton per meter square, means it's an SI unit. So this 1 poise is 0.1 Newton second per meter square. This is SI unit. We should also keep in mind all these conversions, otherwise our calculation will, mathematics of the calculation will be correct, but the final answer will be not correct. So the question is, there are two plates. Oh, something is happening. There are two plates. This is plate 1 and there is another plate as well. The gap between these, this is plate 2, the gap between these plates is 0.5 centimeter. 0.5 centimeter, and it's filled with an oil. The gap is filled with some oil, and the coefficient of viscosity for that oil is 5 poises. Okay. Now to put it in Newton SI unit, 1 poise is 0.1 Newton second per meter square, means 5 poises is 0.5 Newton second per meter square. Now we need to calculate the shear stress, again using the same knowledge that we used in last question. Shear stress means force per unit area, right? So we can immediately connect coefficient of viscosity and this kind of force per unit area. What is the expression we need to use is this. F by, or I can write it like this, F by A is equal to eta dV by, here I'll write as x, because here it's not radius, here is linear distance. So this is the same equation we are using here. So since stress is force per unit area, means stress value I already know, I need to calculate, stress is what, sorry, we have to calculate, okay. So eta is 0.5 and the velocity gradient we need to calculate. Of velocity we have been given, velocity is 10 millimeter per second and the x here is 0.5 centimeter, right? That also, right. Velocity is 10 millimeter per second. Then I'll convert it into meters again. Millimeter is 10 to the power minus 3 meters per second. Actually, I want to write this. 10 times 10 to the power minus 1 millimeter is 10 to the power minus 3 meters. So this will be this. That means 10 to the power minus 2 meters per second is the velocity. Now the x, or the distance, is 0.5 centimeter, again converting it into meter, centimeter, see 100, 0.5, 10 to the power minus 2 meters. Now putting these values here, eta is, okay, already in SI, dV by dx. So from this dV by dx will be 10 to the power minus 2. No, sorry, 10 to the power minus 2. And the final distance is between these two plates is 10 to the power minus 2. And the velocity is like, the change in velocity will be here, this much. And the distance change is 0.5, 10 to the power minus 2. solving this will get cancelled, and so the answer is 1 Newton second per meter square. This is the force per unit area or the shear stress. So you remember, I hope you remember, we had discussed when we were discussing Young's modulus of elasticity and other such elastic moduli. We were talking about when there is a shape like this and we apply some force because of which displaces from its original position, right? This by some angle theta, then that stress is called shear stress. So here also, like, if you can there, if I tell you analogy that liquid is flowing, means the flow of liquid is some, because of some force its shape is changing, right? It's flowing, so there is some force acting per unit area column of that liquid. So there the shear stress, we can also call it its form of stress. Okay, so the answer here was this 1 Newton per meter square. This is the correct answer. Now the next question. The question says a liquid flows through two capillary tubes A and B in steady state. So steady state are connected in series. So there are two capillary tubes A and B. Their radii are different. Say if the radii of this is this and radii, we don't know, that's something different. This is A tube, this is B tube. The liquid is flowing through it. Steady state means the velocity is constant and total force acting on it will be 0. Okay, what we have given is their lengths are L and 2L respectively. So length of A tube is L, length of B tube is 2L, length of A tube is L, and their radii. So radius of A tube is R, radius of B tube is R over root 2. Then the pressure difference across the A and B tube are in the ratio. So the tubes are connected in series. That means volume of liquid flowing through tube per unit second will be same as the liquid flowing through B. Anyway, we are saying it's steady state, means the velocity at any particular point is same. I mean the total force acting on the liquid will be 0. Using the Poisson's equation. So recalling what was Poisson's equation, it was that volume of liquid flowing per unit time is given by this expression pi r to the power 4, the difference in pressure divided by 8 coefficient of viscosity and length of the, this is in general, this is the expression in general. Here we have different I mean the liquid flowing through this, this tube has different radius, this tube has different radius. So since the flow of liquid through tube A, I mean the volume of liquid flowing through tube A is equal to volume of liquid flowing through tube B. Volume of liquid flowing through tube A is equal to volume of liquid flowing through B tube. So from this expression we can rearrange, and from this I will get, so volume per unit time, so time is per unit time, we can ignore that, and what we will get is pi, this radius A to the power 4, and pressure, let's say pressure for this one I am calling it A, divided by 8, and the liquid coefficient of viscosity is same because the same liquid is flowing throughout, so it's just eta, and length of A tube, so this is the expression for volume flowing through this tube A at any particular point of time and particular point of the tube. The same way we'll write the expression for this radius to the power 4, the pressure divided by 8 eta, length of the B tube. Now this will be cancelled, eta 8, this will be cancelled. So we are left with, and we need to find out the pressure difference across A and B. That means ultimately we want to find out PA over PB. So rearranging this equation, I'll get RB upon RA to the power 4, right? This will go in the denominator here, and LA will come to the numerator. This is 4 LA divided by LB. Now substituting the values, radius of tube B is R by root 2, radius of A is R, means this to the power 4, okay, multiplied by length of tube A is capital L, length of tube B is twice L. So this R also cancel. 1 over root 2 to the power 4 means 1 over 4 times 1 over 2 means answer is 1 by 8. So the ratio of pressure is 1:8. This is the answer. This is the correct answer. Now the next question is, calculate the approximate value of coefficient of viscosity of water from the following data obtained in capillary flow method. Water collected, we have been given some value and we need to find out the coefficient of viscosity of water based on these data. So again recalling the formula that we use for eta, this is that formula. Coefficient of viscosity is given by pi r to the power 4. The pressure difference, either I can denote it with delta P or P, it's fine. 8, and this is volume of liquid L. From, okay, now to, this is radius of capillary tube. The answer is in poise, means the answer is in CGS unit. So I'll keep everything in CGS unit. So it's in centimeter, it's fine. Length of tube is also in centimeter, that is fine. Pressure difference 10 centimeter of water column. This pressure we need to change this. Okay, wait. So this is in 10 centimeter of water column, means the pressure value will be, rho g h. So density of water in CGS we can take it 1, or I can substitute it later in the final expression, that's okay. So the radius value is this. Now I'll convert this water flow rate, which is milliliter per minute, okay, I'll convert it into CGS. So we 120 milliliter per minute, so 1 milliliter per minute is actually 1 ml is 1 centimeter cube. Should know this. 1 ml is equal to 1 centimeter cube. Okay, so 1 ml is fine. It's 120 ml will be 1 centimeter cube, and 1 minute is 60 seconds. So when I was, this will be 2 centimeter cube per second. This will be the flow. Now from Poisson's, and density is density of water in CGS unit is 1 gram per centimeter cube. This also we will use later. Now from Poisson's law, this I'll directly substitute. From Poisson's law, we know that volume of liquid flowing per unit time is given by pi by 8, pressure difference r to the power 4, the same thing. I'm rearranging in this form because we need to find out the, we need to, what we need to find out here is yeah, eta only. Then I can just, okay, but just to recall that from Poisson's equation, the volume of liquid flowing per unit time, so per unit time means I don't need to put this T every time here. It's understandable that this is the volume what which is flowing per unit time. So the Poisson's law is this. So from this expression we get, and using this expression, eta will be pi, and radius of capillary tube is 0.25 to the power 4. This is the other information. 4, and pressure is rho gh. I'll substitute its value. So the expression becomes 8, and the volume here, 8. A volume we already have, which is 2 centimeter cube per second, and length of the tube is 50 centimeter. This will be or let me know 0. Solve. I'll calculate them together. Right now, just first let me. So rho is 1, and acceleration due to gravity. Acceleration due to gravity is if it's been given, yeah, it's been given that we can take it as 10 meter per second square. Okay, this is 10 meter per second square. It's given. That means if I put it into centimeter, it will be 1 meter is 100 centimeter. That means to the power 2 per second square. Yeah, so putting these values, 10 to the power 3, and h is 10 centimeter divided by 8 times 2 times 50. Value that I'll get is 0. Which let's see. This was right. Acceleration due to gravity 10 meter per second square. In centimeter it will be like this. This times 4 divided by 16 divided by 50 times, what I'm getting is 0.00001532 times 10 to the power 4. So the answer will be 0.153 poise. So this is the correct answer, 0.153. Like if we round it off 2 and keep it only 3 digits, we'll get 0.153 poise. So this is the correct answer. Okay, now moving on to, these were the questions based on the coefficient of viscosity. Now we need to understand what are the important concept, which is terminal velocity. So what happens is, if we have a container full of liquid and there is a spherical system, anything, spherical shaped body which has been put into it. So if its density is less than the density of liquid, we know it will float, right? But if its density is not less, then it will go inside and it will start, not flowing, it will drop, it will go down in the liquid. And what will be the velocity of that, its motion? So it will be going down in the liquid with which velocity? So here first we need to understand, before understanding terminal velocity, we need to understand two other things. One is buoyant force. So from Archimedes principle, if you recall, Archimedes principle, first I'll read out the statement. Archimedes principle states that the upward force which is exerted on a body immersed or submerged in a fluid, whether partially or fully, is equal to the weight of the fluid that the body displaces and acts in the upward direction at the center of mass of displaced fluid. So to put it in simpler word, what it wants to say is, when we put any kind of body in a fluid, here particular it's a liquid, so I can call it liquid, that's fine. So when we put a body in a liquid, either partially we submerged it or it's completely submerged, so it displaces some amount of liquid from that place, right? That amount, that volume of liquid that it displaces, that amount of liquid puts force on this object in the upward direction. So downward on this object, there is its acceleration due to gravity on its mass. So downward, its weight is pulling it down, but the amount of liquid it's displacing, which we get to know from Archimedes principle, that it displaces the amount of liquid that it displaces, that volume of liquid exerts a force on it on the upward direction, and that force is what we call buoyant force. That means when a body is immersed or submerged in a fluid or liquid, there is a force acting on it upward, which is called buoyant force or buoyancy. The another kind of force that acts when a body is dropped in a fluid or a liquid, that we get to know from Stokes' law. And okay, so first let's understand Stokes' law. Stokes' law states that the force that retards a spherical body or a sphere moving through a viscous fluid is directly proportional. So experimentally it has been found out by some researcher named Stokes, I think, and the law has been given by him. This law is for a spherical body only. Okay, so these laws that we have been discussing, they have been particularly derived for a particular kind of body. So the Stokes law states that the force retards a spherical body. As we can see here, this is a spherical body, it is moving through this liquid, and one we understood is buoyant force acting on this body upward. Okay, one is buoyant force acting on it upward. There is another force that will be, because it's moving through the viscous liquid, we understood right earlier when we were deriving Poiseuille's formula, that because they are flowing, they are experiencing viscosity, and that leads to that is the cause of the viscous force. So that viscous liquid is exerting viscous force on it, and the dependency of the force is, it depends on the radius of the sphere. It is proportional to the coefficient of viscosity of the liquid, and it's also proportional to the velocity of that spherical body. So what if we write it in mathematical form, then the viscous force, I'm writing it with, denoting it with FV, subscript V. So due to this viscosity, the force is viscous force is experienced by the spherical body, which is also called the drag force. It's also called viscous drag force. Okay, it's also called the viscous drag force or viscous force or drag force. They all mean the same. When the body is moving through the fluid, it experiences viscosity, and that leads to viscous force. So this viscous force, experimentally it has been found out, is proportional to the radius of that spherical body, coefficient of viscosity of that fluid, and velocity of this velocity with which this body is moving in the fluid. Also experimentally it has been found out. So I mean, if I'll replace this proportionality constant then there should be some constant value here, right? I mean, this proportionality sign, if I'll remove and I want to put equal, that means I need to put some constant value here. So after doing some sort of experiments, it has been found that for spherical body the value of k is 6 pi. So for a spherical body moving through a viscous liquid, the formula becomes 6 pi eta r v, and this is the equation of Stokes' law. So this is also a force that is acting on a body when it's moving through a fluid. So we understood here two kind of forces, and another kind of force we know due to gravitational force. I mean, the acceleration due to gravity acting on the mass of body, it's anyway pulling it towards the earth. So that one force is there. So now it will help us to understand and derive the value for terminal velocity. So again, a spherical body, I have kept, like, I just dropped it from top of the, imagine this whole container is filled with liquid. I just dropped the spherical body from here, and it has moved till this position, and at any particular time I want to know what are the forces acting on it. So at particular time, say t, there is force that we can call, so okay, let me just define the statements I have written here. Terminal velocity is defined as the highest velocity attained by an object falling through a fluid. So when an object is falling through a fluid, like a situation as this, terminal velocity is the maximum velocity it attains. It is observed when sum of drag force, so this is the drag force, right? The body is moving, it's experiencing viscous drag force in opposite direction, which is given by Stokes' law. This is the expression here. So drag force is the Fd is the drag force, and buoyancy is buoyant force, the volume of liquid displaced by this spherical body will exert force upward, which is given by this expression Fb. When these two forces are equal to the downward gravity force acting on the object. This is the downward gravity force acting on the object. So when they all get balanced, or they all I mean, the net force on the object, when it becomes 0, then the velocity of this object, of this spherical body, becomes constant, and it becomes maximum after a certain time, and that maximum value is what is called as terminal velocity. We can denote it with this v with subscript t. So how do we get this expression is, this last sentence says the acceleration of the object is 0 as the net force acting on this object is 0. So net force, I mean, they get cancelled, and the net force on the object after a certain time, immediately when I drop, it may be more, that's why it may be accelerating, but after a certain height or a certain depth of going inside the liquid, all the forces become 0. That means the acceleration becomes 0. That means the velocity becomes constant, as we had discussed in a few slides back. That means if I write the equation, it will be the drag force, which is acting upward, plus the buoyant force, which is also acting upward. It's equal to this gravity, downward gravity force acting on the object. So everything becomes 0, means if I bring it left side, all the forces acting on it will be 0, right? This is Fd plus Fb minus Fg. All the forces acting will be 0. Or I can write it like this: upward force is equal to downward force. That means no acceleration is happening. So from this, when I put the values here, from Stokes' law we already know this is the expression for drag force, and the expression for this is actually, this is basically the volume of liquid displaced, right? So mass of that liquid will be, so mass we know density times volume. So this is spherical body, so volume will be 4 by 3 pi r cube, and sigma here is the density of liquid. Let me write here somewhere. Sigma is density of this liquid, and rho is density of this spherical body, as you can see here in the diagram. So drag force in these expressions, when I will substitute, 6 pi eta rv plus 4 by 3 pi r cube, the density of the liquid, this will be equal to, Fg will be 4 by 3 pi r cube. Now this is the density of the spherical body, whatever material it is made up of, times the g. G anyway will be same. Now when I solve this, we don't need to do, let's save some time. I'll directly just tell you the expression, the final expression, the velocity that we'll get, because, or okay, just one more step we can write. Okay, when this will come right inside, 4 by 3 pi r cube, also I can take common, g also I can take common, sigma, sorry, that will be rho minus sigma. Yeah. So from here the velocity will be all this 4 by 3 pi r cube g rho minus sigma, this whole thing divided by 6 pi eta r. Solving this, all this 6, 4, 3, everything, this will get cancelled, this r, this will become square. The final expression that I will get is 2r square g is rho minus sigma divided by 9 eta, and this will be a constant velocity with which the body will be dropping in the liquid, and it will be the maximum velocity that the body will attain, and this is what is called terminal velocity attained by the body when it's moving in a viscous, or in a, viscous, a fluid or liquid. So this is the expression of terminal velocity. Now we'll do some questions based on this. So for this we needed to understand Archimedes' principle, the buoyant force, and the drag force expression that we understood from Stokes' law. Yeah. So now let's do some questions based on this concept. First question is, consider two solid spheres P and Q of density 8 gram per cc and diameters 1 centimeter and 0.5 centimeter respectively. Sphere P is dropped in a liquid of density 0.8 and viscosity Poissons. Okay, so it's a question of again a spherical body being dropped in a liquid. So there are two solid spheres, sphere P and sphere Q. They both have same density. Okay, so they both have same density, and the density is 8 gram per centimeter cube. They have same density, 8 gram per centimeter cube. The diameter of this, density I'll denote with rho. Okay, density I'm denoting with rho to avoid confusion, and diameter is 1 centimeter. That means radius will be 0.5 centimeter. Here the diameter is 0.5 centimeter. So the radius will be half of this, 0.25 centimeter. Sphere P is dropped in a liquid of density 0.8 gram per cc, whereas sphere Q is dropped in a liquid of density. So these two spherical bodies are dropped in different liquids actually. So we have been given the density of those liquids. So sphere B is dropped in a liquid whose density, so this sigma I am using to denote the density of liquid. Okay, so this for P is 0.8 gram per centimeter cube. All the things are in CGS, so I think final answer we'll keep in CGS. Sigma for this liquid is 1.6 gram per centimeter cube. Viscosity, viscosity for this first case is 3 Poissons. If you remember, Poissons is a SI unit, and everything, I mean, apart from this coefficient of viscosity, everything is in CGS. So we'll conveniently convert this also in CGS. So one poise is, if you remember, I had told that one poise, which is a CGS unit, was equal to 1 Newton second per meter square. I think this was the thing. Yeah, or 1 Poisson. This is the, no, sorry, 0 0.1. 0 0.1. 0 0.1. That means 1 Poisson will be 10 poise. So this will be 30 poise in CGS. And the eta, sorry, the eta here will be, the eta here is 2 Poissons. That means 20 poise, right? Now we need to find out what the ratio of terminal velocity of P and Q. Okay, so recalling that terminal velocity is given by the expression 2/9 density of body minus density of liquid times r square times acceleration due to gravity divided by divided by eta. So using this expression of terminal velocity, the terminal velocity of P, the terminal velocity of P, the ratio of terminal velocity of P and to the terminal velocity of body Q will be, I'm directly writing because 2/9 it's a ratio, so all these constants will cancel out. We'll be left with, okay, so density of both the solid spheres is same, so we'll just write rho minus density of liquid, this will be P, the radius is different, so this will also stay, G will also get cancelled, right? So ratio. And then this eta, okay, eta will come here, that means eta of Q because it's in denominator, and this is just for lack of sufficient space I'm directly doing, or if you want, okay, let me try to, so the expression here will be eta P, let's see, I'll take new slide in that case. So this divided by the terminal velocity of body Q, RQ square. The other things are already cancelled, so that's why I didn't think I would write, but just to keep everything, no confusion, so I'll write like this, okay. This is basically, I'm taking ratio, means I'm dividing these expressions like this. And in this case, this is what I was saying, these are just constants, same for both the bodies, so this will get cancelled, and then will be this minus sigma P RP square, and this eta Q will come in the numerator, right? This is eta divided by sigma Q RQ square and eta E. Substituting these values here, 8 minus 0.8 and P 8 minus 0.8 and Rp is 0.5, 0.5, or I can write 1 by 2, or okay, its square will be 0.25, 0.25, and eta q means 20 divided by this 8 minus 1.6, 8 minus 1.6 times what is the radius here? Oh, I should have written it. There are different values, right? Rp and Rq. This will also be P, sorry, Q. This will be Q. This will be P. Okay. So the value Rq is 0.25. Square of 0.25. Okay, whatever it is, I'll calculate. Times 30. So what I get here is, if I'll calculate, when I calculate this, I get 8 minus 0.8, 7.2 times 0.25 times 20, 36. Numerator becomes 36 and denominator 8 minus 1.6, which is 6.4 times 30 times 24, 25. Oh, so it becomes 12. So this will be 3, right? So the ratio is 3:1. This is the, as was asked in the question, we needed to find out the ratio of terminal velocity for these two solid spheres. So the ratio is 3:1. Now the next question. Here the question says 8 drops of a liquid of density rho and each radius of A are falling through air with a constant velocity of 2.5 centimeters per second. When the 8 drops coalesce to form a single drop, the terminal velocity of the new drop will be. Terminal velocity again. So the formula is like the first thing. I'm writing the expressions so that we know what all the parameters we need to find out. So terminal velocity, to calculate terminal velocity, this is the expression. I need the density of the body, density of liquid, which in this case is air, acceleration due to gravity, divided by coefficient of viscosity of the air again, and the radius of the spherical body, square of it. So that means I need these density values, coefficient of viscosity, G I already know, the value I already know, and the radius. So what it says is for that we have not been given the radius of this big drop, but we have been asked to calculate terminal velocity for this. So how we will get the value of radius for this single drop? That we can get from here. What we have been given the information is that 8 drops, okay, there's some small 8 drops, they are all falling in the air with their radius is A actually, okay, and their density is rho, and they are 8 in number. They are falling with constant velocity, that means it's a terminal velocity of 2.5 centimeter per second. And then what happens, due to some reason they all merge together to form single big drop. Of course the radius will be more because all volume of 8 these small drops will merge to form a drop of bigger volume and 1 in number. So its radius we need to find out. So the volume, since volume of these 8 small drops is equal to volume of this big single drop, so the equation, we can equate these two volumes, right? I'll call this small. So volume of small drops, one single drop volume times 8 because there are total 8 number of these drops. This volume will be equal to volume of the big drop, this single drop, this big drop. Okay, I'm calling this B and I'm calling this S because these are small, this was big, so I'm denoting it accordingly. Okay, so the volume for this 4 by 3 pi r here is a cube times 8 is equal to volume of this 4 by 3 pi r, let's call it B, that radius of big drop. Okay, 4 by 3 pi r cube is 4 by 3, 4 by 3 will be cancelled, so the value of RB cube is 8a cube. That means the value of RB is cube root of this. Cube root of 8 is 2 and cube root of a cube will be a. That means we got one parameter from here. The radius of the big drop will be twice of a. Now this we understood, it will be 2a. Now substituting this here, this is say the terminal velocity of the big drop, so B, density of both, since the drop are made up of same liquid, density for both will be same. Density of air will also be remain same, G will remain same, eta will remain same. Okay, only this radius now we need to take care. So I'll denote it B by B to show that it's radius of the bigger drop, and substituting the values 2g by 9 eta. We are trying to find out some relation between the terminal velocity of this big drop and the terminal velocity we have been given of the small drops. So if we are able to establish relationship between these two terminal velocity, we can find out easily, because these value of density we have not been told. Anyway, so this will be 2g divided by 9 eta and rho minus sigma, and RB is this 2a. So squaring this, it will be 4a square. And for this small drop, the terminal velocity will be 2g over 9 eta rho minus sigma and a square, because its radius is a, right? So this will be the expression of this small drop terminal velocity. If you compare these two, you can see that this part is same as this is the value of terminal velocity of the small drop. That means I can substitute here, this is terminal velocity of small drop times 4. Now terminal velocity of small drop is 2.5 centimeter per second times 4. That means 2.5 times 4 means 10. 0.5 times 4 means 10. Yeah. So 10 centimeter per second is the terminal velocity of the big drop. So the correct answer is option D. Okay, next question is this. Two raindrops of radius r and r by 2 arriving at the ground will have their terminal velocities in the ratio. This is also very straightforward. So there, let's call this drop 1. There is another drop, let's call it 2. Their radius of drop 1 is r, radius of drop 2 is r by 2. They are coming, it seems they are made up of same material and everything. Again, what is the formula for terminal velocity? It is given by 2 by 9 eta. In numerator we have g, then density of body, density of liquid, and r square. This is the expression of terminal velocity. That means if I'll take ratio of terminal velocity for this, let's call it Vt1. For this, let's call it Vt2. So the ratio Vt1 to Vt2 to G9 eta, all these are constants. This density of liquid also will be same. So what's the only thing change will be the radius. So radius will be radius of first body to the radius of second drop. And what are those radius? R1 is R, so square of that, and R2 is R by 2. So R square by 4. Solving this, 4 R square by R square, that means 4:1 would be the ratio of terminal velocities of these two drops. This is the correct answer, answer C. Okay, next question is the terminal velocity of a copper ball of radius 2 millimeter. Okay, let me write here. This final answer again is in SI unit, so we'll correspondingly convert them into SI units. So first thing is copper ball is of radius 2 millimeter we have been given. I'll convert it into meters. Millimeter is 2 times 10 to the power minus 3 meters, right? 1 meter is 1000 millimeter. Yeah. Falling through a tank of oil is this. So this is the terminal velocity of this copper ball, which is falling through a tank of oil. So terminal velocity of this ball is 6.5 centimeter per second. Converting it into meter per second, it will be 6.5 10 to the power minus 2 meters per second. Compute the viscosity. So we need to compute coefficient of viscosity, and we have been given density of oil, sigma. Density of liquid we denote with sigma. So density of oil is 1.5 times 10 to the power 3 kg per meter cube. And density of copper, which is the ball is made up of copper. The density of copper also we have been given an SI unit, 8.9 times 10 to the power 3 kg per meter cube. We need to find out coefficient of viscosity, and terminal velocity we have been given. So using our terminal velocity formula and then rearranging it, the terminal velocity formula is 2g by 9 eta rho minus sigma r square, right? So from this, what I want to find out is eta. So taking it up, I get 2g sigma r square divided by 9 times the terminal velocity. Now substituting the values, g is 9.8 meter per second square, density of body is 8.9 times 10 to the power 3 minus density of liquid is 1.5 times 10 to the power 3 kg per meter cube, and then radius, square of radius is this 2 times 10 to the power minus 3 meter, square of that. This whole thing divided by 9 times the terminal velocity, which is given, the value is given to be 6.5 times 10 to the power minus 2 meters per second. So the final expression will be 8.9 minus 1.5 will be 7.4. 4 times 2 times 9.8 8.9 minus 1.5 is 7.4 times 2 times 9.8 times 4, 5, 580.16, and these will be 10 to the power 3 minus 6. From here we'll get 10 to the power minus 6 divided by, this will be 9 times 6.5, that will be 58.5 times 10 to the power minus 2. This is in exponent, okay? 3 minus 6 this is. So this will give 580.16 divided by 58.5. Answer will be 9.91726. Okay, I'm just writing for time being till 5th decimal digit because we need to take care of these powers also. 3 minus 6 means minus 3, and this 2 will go up, means the final thing will be 10 to the power 3 minus 6 plus 2, right? This means 10 to the power minus 1, means this decimal point will come to the left, 0.99173, or up to whatever decimal digit. This will actually, this can be rounded off to 1 Newton second per meter square. So the correct answer here will be option C. Should be the correct answer for this question. Okay, so these were the questions based on the motion of body in a fluid, where we understood Stokes' law, coefficient of viscosity, Poisson's law, terminal velocity, and then we did problems based on these concepts. Now, another experiment that were done in the last week's lecture was based on oscillations, pendulum. Specifically, the experiments were based on a simple pendulum. So first let's understand what's oscillation or what's simple harmonic motion. So we, again, these things we have studied, like what is periodic motion, which repeats after certain time. I mean, the body comes to same position after particular that same amount of time, then that kind of motion is called periodic motion. But then what's simple harmonic motion? So simple harmonic motion is a special type of periodic motion. Here also the body comes to the same point after certain time, but in this a particle moves to and fro repeatedly about a mean position or equilibrium position. So like if I give you example, general periodic motion is like a very common example is the planet moving around the sun. So they come to the same position after, like Earth comes to same position after 365 days, right? But that is not a simple harmonic motion, because simple harmonic motion, in simple terms, if I say, it's in this a particle moves to and fro about the mean position, and later we'll see the expressions which are also important for a motion to be defined as a simple harmonic motion, that we'll see now. But here okay, I have written here that like in this example, if we see, this is simple pendulum, this is the point of suspension, right? This is the point of suspension where it's fixed or hung. This is massless thread. We consider, basically we don't consider the mass of this thread or string with which this bob is attached. We just consider whole masses in this bob, and when we take it to some height and leave, it will do this to and fro motion about this mean position. This will be our mean position, and it will go right and left about this position, and this we call simple harmonic motion. So as we know, when I will take this body to this away from equilibrium, there will be mg working on this bob downwards, and there will be tension acting along this string, and if this angle is theta, that means This angle is also theta. This means this component, if I put it into these cos theta sin theta components, this will be mg cos theta, this will be mg sin theta, right? So what basically is that these forces balance, and there is, I mean, these forces, there is restoring force. The force mg is acting downwards, but its component one is balancing the tension force and the other one will drive it to its equilibrium position. This force, as you can see, its direction is towards the equilibrium point. Again, when this body will go to this left side, the this restoring force will be acting to the right, again towards the mean position, but the body will be moving towards this direction, but the restoring force will try to pull it towards the mean position. So, say in simple harmonic motion, the restoring force is directly proportional to the displacement. The force is directly proportional to whatever the displacement is. Like in simple pendulum, the displacement is in theta. So let's write theta. It's proportional to the displacement of the body from its mean position, and its direction of this restoring force is always towards the mean position. Like here also, restoring force is acting towards this mean position. In another case, like the spring system, the spring mass system, here the displacement was in terms of angle, here the displacement will be in terms of, we can say x, like there will be some linear displacement here. Here it was angular, here it will be linear displacement. So if I stretch this away from its equilibrium position to its right, like shown here, and then I leave, again it will go to some position here, right? And again it will go to right, again it will come back until it stops completely. So this again we see it's doing to and fro motion about this equilibrium position. So in this case it was proportional to theta. Here we can say the force, restoring force, is proportional to this displacement x. But the direction is, again in this case also, its direction of restoring force is opposite to the direction of displacement. The displacement, if it's happening in this direction, restoring force is in this direction. If the body is, the spring is compressing and the body is going in this direction, restoring force again will be in opposite direction. So this is what is important about simple harmonic motion, and how it's different from just being a periodic motion is that simple harmonic motion, the restoring force in simple harmonic motion, it's always towards the direction is always towards the mean position. We'll see the mathematical expression also. So this is about oscillation. Now because the experiments that were done based on simple pendulum, there were three types. First we'll you must have already watched the videos where the professor explained how we can do those experiments. First, just understand what's there are three types of oscillations experimentally we can do with a pendulum. One is free oscillation, another is damped oscillation, third one is forced oscillation. So first let's understand what's free oscillation. So free oscillation possesses constant amplitude and period without any external force to set the oscillation. In such a system, amplitude, frequency and energy all remain constant. So as we saw in this case, if we have a pendulum suspended with a massless thread like this, then if it's in a vacuum, say the system, this same pendulum system is in a vacuum, and say I have displaced it, whatever this motion is happening, okay, this, imagine this is in a vacuum. In vacuum there will be no air. Just now we talked about viscosity, right? That when a body moves in a fluid means it could be gas, that is it could be air, or it could be fluid. So when a body, viscosity, spelling is not correct, let me just, so if this pendulum, I place it in a vacuum, then there will be no air, that means no air particle, that means no viscous force. If there will be no viscous force, then whatever initially if I took it to this position and left, then it will keep on doing this motion. It will never stop. At this position, all it gets all the potential energy, right? And at this position, all the potential energy converts to kinetic energy. Again, in this position, all energy is form of potential energy. In between, it's some part of potential energy, some part of kinetic energy. So as we know, law of conservation of energy, that energy can neither be created nor destroyed. So basically, if you have initially given it some energy, that energy will keep on converting from potential to kinetic, but it will never be lost because there is no viscosity. So though there will be no frictional energy, I mean there will be no loss in form of friction. So this pendulum will keep on moving forever, it will never stop. This is what is called free oscillation. If I draw it in form of wave, like with time, if I have just started at t is equal to 0 from here, at time t is equal to 0, say I took it till here and left, then the amplitude of this, the amplitude, if I, it will be in this form. Later we'll see how we get these sine and wave, but just to show this, because you must already recalling about these things. So it will be a sine or cos wave depending on, there are some conditions, but it will never stop, it will keep on going. So this happens, when this happens, it's called a free oscillation. But now we know, when the same experiment happens in our experimental lab, then there is no vacuum, there is air particles, there is air resistance or viscosity. Because of this viscosity, there is viscous force, and eventually this motion of simple pendulum, it will come to stop. I mean, first it was, if it was initially going up to this, if the amplitude was going to this, then after some time maybe it's not going this high, it is just going up to this position, and then even less amplitude, and then finally it comes to this position at the equilibrium, finally it stops. Why this happens? Because the energy of this motion, kinetic energy, potential energy, it's converting, but also some form of energy is getting dispersed in to overcome the air friction or the viscous force due to the air. So this, when I plot with amplitude versus time, we can see initially the amplitude would be high, after some time it will come, it will be lesser and lesser, and eventually it will be 0. So this type of oscillation is called damped oscillation that we usually see around us. Free oscillation is an ideal case that cannot happen in our experimental lab until we have a vacuum, but damped oscillation is what we see around us. So damping is the resistance offered to the oscillation, and this happens because of the air resistance. Now the third kind of oscillation is forced oscillation. So free oscillation, we just once gave it some energy, like we displaced it, and then it sustained itself. In damped oscillation, once we gave it some energy or we displaced it, and then first it keeps oscillating, but eventually it stops because of air friction or viscous force. In forced oscillation, we have a pendulum or we have a oscillating body where we keep on supplying some force to it periodically, so that eventually it will, because again it will start damping, but because we will keep on giving it some force, so it will not come to stop, it will not stop, it will keep on oscillating. So there this kind of oscillation we call forced oscillation, and this external periodic force because of the external periodic force that we are supplying, this kind of body keep on oscillating. Here the amplitude of oscillation experiences damping but remains constant due to external energy supplied to the system in form of external periodic force. For example, a good example to understand this is when a person is on a swing. Okay, I should not draw the diagram, it won't be good, but yeah, if a person is on a swing and the other, his her friend, after a certain time, when he sees that the swing is slowing down, he'll again push, give it a push. So in that kind of push is actually a form of forced external periodic force. So the swing will keep on moving. So this is a real life, I mean the usual example that we see around us. This is a form of forced oscillation. Now the instrument that was used in, and the professor showed experiment based on this instrument for doing this oscillation. This instrument is called Pohl's wheel or Pohl's pendulum. This is the spelling. This is Pohl's pendulum or Pohl's wheel. It looks like this. This is the wheel. Here, say if this is the marker, and if it's oscillating means this will go up to say some this height, and then in this direction it will go to some same position. It will keep on oscillating about this mean position. This is mean position. It will keep going right and left on this if we once started. So that will be free oscillation. It's just like the simple pendulum case. But here also we can do the damping oscillation as well as the forced oscillation. How we do it is this, the simple oscillation we don't need to do anything, but for damping this oscillation we'll provide damping by using eddy current. So if you recollect or recall, when a metallic body, when a metallic body is kept in a magnetic field, say this is a metallic body and this is some field, field is here, and we change this magnetic field, either we make it alternating or we make the body to move in this field. So what happens is the magnetic flux related to the body will change. If there will be change in magnetic flux, that leads to, we know that leads to EMF generating. So that will lead to current induced in this metallic body, and since there will be current induced, there will be magnetic field, and that magnetic field, from Faraday's law, we know that magnetic field will oppose the origin, oppose the change in magnetic flux that was causing it. So what will happen, some way we need to change the magnetic flux. Say if in this we are moving this body from right to left, because of that the magnetic field is constant, but we are changing, we are moving this metallic body. So the magnetic flux associated with the body will change. Because of that, current will be induced, and because of those current, there will be magnetic field in the body which will oppose the change in magnetic flux, and that oppose will reduce. How it will oppose? It will stop the velocity of this body. Eventually it will try to stop the motion of this body to stop the change in magnetic flux. So this is a way of saying that the motion is getting damped, right? Initially we are moving it, but because of the eddy current induced, these currents are called eddy currents, because of the eddy currents induced in the body, the motion is eventually getting damped. So this is a way that is used in this Pohl's pendulum to damp the motion. Like we give current here, this is one side of the magnet, on the opposite side there is another magnet, so one is north pole, another is south pole. This metallic circular disc that you are seeing is metal. So when this metallic thing will move, as we say, when we start oscillating, it will move to and fro, right? If it's moving to and fro between this magnetic field line, so there will be magnetic flux change, and there will be eddy current, and this will oppose the change in magnetic flux, means eventually this oscillation of this disc will come to stop. So this way we can perform the damping oscillation experiment in this same instrument. There is another there is another experiment that was based on forced oscillation. For that, using some external source, we can give supply some periodic force to this so that the oscillation keep on going. Now seeing the okay. So the pole's pendulum, actually it's also rotating pendulum, because you can see here it's rotating, and it's also called torsional pendulum. It allows for investigation of simple harmonic rotary oscillation. The only forces acting on the wheel are the restoring torque provided by spiral spring and damping torque supplied by means of an eddy current brake with an adjustable current. So we can change the amount of current. Based on that, we can change the damping value, how fast or how slow it will get damped. So to do these three kind of experiments here, we use this Pohl's pendulum or Pohl's wheel. Now if I to give you quick expressions to find based on these, I should have given here it's so this just we understood the theory. Now to write the mathematical expression for these oscillations, the equation of motion for free oscillating body, the differential equation will be given by the equation of motion for this will be given by, if say the x is the displacement, then the equation of motion for free oscillation will be d2x by dt square plus omega naught square x is equal to 0. And the solution for this solution will be xt is equal to some amplitude value and cos omega naught t minus phi, where phi is the initial phase of the oscillation and omega naught t is the natural frequency. So this will be the solution for the free oscillation differential equation. Now for the damped oscillation, the equation will be, we'll have a damping factor here. Like earlier, we'll have an acceleration expression, the factor d2x by dt square, this is acceleration, plus 2 beta, here the beta is the damping factor, dx by dt, that is the velocity, plus omega naught square x is equal to 0. This is the differential equation of motion for damped oscillation, and the solution for this will be, this is amplitude, say e to the power minus beta t. So because eventually it dies down in this decay is exponential actually. This decay, as you can see, is exponential, and that depends on this damping factor beta. So the solution is, this xt is a naught e to the power minus beta t, and again this cos omega t angular frequency plus phi or minus phi, where this omega is different from natural frequency. Now it's damping, so the frequency is different, and beta is some damping coefficient or damping constant. Here the amplitude, this amplitude can be given by this maximum amplitude. Like if I take it to this extreme position, that will be its maximum amplitude. After that, these amplitude will keep on decreasing. So if this is the maximum amplitude, then amplitude at any particular position will be given by this expression 1 plus beta square by omega square, and this phase phi will be given by tan inverse minus beta by omega, and this omega will be given by this. This is the natural frequency of oscillation of this symbol pendulum, and this will be after damping. So this is the expression. So this will be positive. Now the differential equation, the equation of motion for forced oscillation, the equation will be given in this form: d2x by dt squared plus twice beta. This is the damping term again. When it's free oscillation, anyway we don't need to give it anything because it will not stop, but here the damping term is there, and if we give this as the natural frequency. Now this is the force, external force that we are supplying to the oscillating system. This is usually in the form of a periodic force. There's this force which is time dependent. It could be periodic, so it could be of this expression. Now solution for this, after solving this differential equation, the solution we'll get is x will be some amplitude a. I'm just denoting it, can be anything, a prime, a bar, anything is fine. Cos, this is nothing. So a cos omega a t minus alpha. This omega a is frequency of applied force. This should be a, I think. Frequency, the force being applied is in, let me write it properly. The force that we are applying is periodic, right? And that periodic thing is also has angular frequency, we are denoting as omega a. Omega a t. So this is the angular frequency of Ft, the applied force, right? Here the amplitude, expression for amplitude will be given by this maximum force divided by omega naught square minus omega a square, this whole square. This you will get after solving. You don't need to do it here for our experiment. 4 beta square omega a square. This whole thing is under the positive root, and on numerator we have f naught. This is the expression for amplitude, and alpha, you can, the phase, sorry, this is also the phase represented by alpha here. It will be tan inverse 2 beta omega a divided by omega naught square minus omega a square. This will be the phase, and for fixed value of f naught, amplitude a, the maximum value of the amplitude of oscillation, it will be maximum when this this omega a is what, the periodic force that we are applying, its angular frequency is given by omega a. So if this omega a becomes equal to the natural frequency of this system, then this expression will become 0, right? And the amplitude will get its maximum value. So that time it's called resonance frequency condition, or resonance condition it's called. Okay, we get resonance when omega naught, when this omega a becomes equal to or almost equal to omega naught. In that condition, this amplitude becomes maximum, and we see the oscillation becomes, the amplitude of the oscillation increases. That is the resonance condition. Okay, so these were the theory based on this. Now let's solve some questions based on the understanding of oscillations. First question is, a particle is undergoing simple harmonic motion and its equation of motion is expressed as y is equal to 0.1 sine omega t. Okay, so just to recall this also, that when we solve here, we had seen, wait, yeah, for free oscillation we saw, right, the solution is in form of a cos omega t minus phi, or we can, this phase if 90 degree, then this can also be written as a sin omega t. So cos sin both are fine. So this is the form of solution for this. So the displacement, there I was using the variable x, here it's written y, it's the same thing, it denotes the displacement basically. So comparing this with the standard equation, like if this is amplitude, this is displacement, omega is angular frequency, t is time. This is the usual equation right now. Comparing with this, oh no, this will confuse with acceleration. So I'll just keep capital A. I'll use capital A for amplitude. It shows that amplitude is, the value of amplitude is 0.1. The maximum speed it achieves is, so V maximum is 1 meter per second. Find the time it takes to reach from the mean position to half the amplitude. Okay, so let's visualize like this is some simple harmonic body. I'm just taking it to be a simple pendulum, and let's see, this is its maximum position. Okay, this side also it will go to the same height, and we know that velocity at this position becomes 0, right? The amplitude is maximum here, amplitude is maximum at this position, but the velocity becomes here 0, and then the body again starts coming towards the mean position. So okay, I'll tell you one more thing. If we take derivative of this expression, okay, I'll clear it, it will be useful in subsequent solving of subsequent problems. So if I'll take derivative on both sides, dy by dt, the this will give me a omega, sine will be cos omega t, right? This will be this, and if I take it this again, it will give me d2y by dt square, which we know is acceleration, and this will be a omega. Derivative of cos is minus sine omega t, and from here we'll get omega, so this will become square. What this shows is that acceleration is minus omega square, and a sine omega t is y. What this means is acceleration is opposite to the direction of acceleration is opposite to the displacement, and its dependence on displacement is like this. So when the body is moving to right, acceleration or the restoring force is working on left side, and same for when it's moving to this side. So this is the expression. So this will be useful later. Right now we'll just calculate it here. So we have been given velocity. Now from this equation here, okay, using this equation, dy by dt is what? Velocity. So velocity, which is a omega cos omega t, its value will be maximum. V will be maximum when, here you see it's 0 at extreme displacement, but its value is maximum at the mean position. Its velocity is maximum. So velocity will be maximum when amplitude is amplitude value will be same. Okay, this in expression will be the same, but the cos, when this cos will be maximum value, when we will get cos in maximum value, cos 0 degree is 1, and 1 is the maximum value we can get with cos. That means the maximum value from this expression we can get is a omega, right? from this value, since we know V maximum is 1 meter per second, we can calculate from here, or we can use it later also, but okay, let me calculate. From this expression, the value of omega will be 1 meter per second divided by amplitude value, which we know is 0.1, right? 0.1. This will be 0, sorry, this will be 10 radian per second or 10 per second. This will be the value of angular frequency. Okay, so what we have to calculate it, we have to calculate the time it takes to reach from the mean position. This is the mean position. This is the mean position. From here to reach half the amplitude. So maximum amplitude is here. Half the amplitude means somewhere here. Somewhere here. If I keep this in this equation, what we'll get is, for displacement is equal to for half the amplitude, if I keep in this equation, we'll get A in this equation. A by 2 is equal to A sine omega t. Okay, A by 2, A we know, okay, this will get cancelled, that means half sine omega t. Omega we already have calculated, it is 10, but wait, let me do it. Let's take sine inverse of half is equal to omega t. Sine inverse of half actually is 30 degree, and 30 degree, when I write it in form of radian, it will be pi by 6. Omega is 10 and this is t. From this we can calculate t to be, t will be pi by 60. Pi by 60 seconds will be our answer. Yeah, okay. So now the next question. Particle executes a motion given by this expression. Select the wrong statement regarding the same. Is the particle, is it a simple harmonic motion or not? First, let's do some algebra and simplify it with our known form of equation, right? We know that for simple harmonic motion we define displacement. Okay, let's here keep it as x, the displacement with capital X. Then it is either some amplitude A sine omega t and some phase also you can keep, or it can be in the form of A cos omega t, again with some plus or minus phase value. Yes. Okay. So if you remember, cos square theta plus minus sine square theta is equal to cos 2 theta. Okay, so using this identity, we can change this equation to x is equal to A. This cos square omega t minus sine square omega t will change to cos 2 times theta, here will be omega t. Okay, so this if you compare, this comes in the same form. This is amplitude, this angular frequency here has become 2 omega, but and the phase is 0 it seems, but it comes in same form. So we can say that yes, it is simple harmonic motion, but it's simple harmonic motion with period. Wait, this is the angular frequency. The angular frequency here is 2 omega. That means the time period which is 2 pi by frequency, that will be 2 pi by 2 omega. It will be pi by omega. So the time period, it is simple harmonic motion with time period pi by omega, but there are also questions about the displacement at this. So what will be the displacement? So the expression is this: cos 2 omega, and at time is equal to pi by 2 omega. Cos pi is -1. Okay. So which is the correct statement? Is a simple harmonic motion with time period pi by omega? Oh, they have asked which is the wrong statement. So this is the correct statement. It is a simple harmonic motion with frequency 2 omega. Frequency is 2 omega, that is correct. It is a simple harmonic motion with amplitude 2a. It is a simple harmonic motion with amplitude 2a. So it's not with amplitude 2a. It is a simple harmonic motion with displacement 0 at t. This is also not correct. So I mean these both statements are wrong here, because the displacement is not 0 at t, time is equal to pi by 2 omega. So these two are correct, these two are incorrect. Now the other question is about a spring balance. So there is a spring balance that, so spring balance, just to give you reference, that it looks like this. It's also used for measuring the weight of a body. So we hang the body from here and there's a spring inside. Depending on how much the spring expands, we get to know the weight of the body. So this is what a spring balance means. So here in the question it said the spring balance has a scale that reads from 0 to 50 kg. The length of the scale is 20 centimeter. A body suspended from this balance when displaced and released oscillates. So like we see in spring system, right? Like if it's there is a spring which is inside this inside this spring balance, and if I hang a mass and suddenly it will I mean when I hang it, it will the length of the spring will deviate from its equilibrium length, right? It will extend, and when I'll suddenly remove this mass, then it will start doing to and fro motion about this mean position. So we need to find out when that happens, when it's oscillating, and its time period of oscillation also has been given. What is the weight of the body? We need to calculate what is the weight of the body. Okay, so let's start first with this. The force acting on this maximum force on the spring. What would be the maximum force of the spring? Since it's given that it has a scale from 0 to 50, means the maximum force that can act on this spring balance is, the maximum force, gravitational force that can act on this will be maximum mass that is allowed, which is 50 times, and the acceleration due to gravity, it is 9.8 meter per second square. Multiplying this, we'll get 490 Newton. This is the maximum force acting on the spring. Now we know from Hooke's law, force is equal to minus kx, where k is the spring constant, right? Now since force is equal to mg, the spring constant here will be, if we ignore this negative sign, because it's for direction, it has nothing to do with the value of magnitude. So spring constant will be f by this x, or this, the maximum x here could be, the maximum extension in length here could be the maximum length. The length of scale is 20 centimeter. So x maximum, here the x maximum is the length of the scale, which is 20 centimeter. I'm just calling it f by L, which is actually mg by L. So spring constant, the expression of spring constant will be this. Now from oscillation, for case of oscillation, we know the time period is given by 2 pi under root m by k, right? Now time period we have already been given, we need to calculate this m, and we have already, using Hooke's law expression, we have found out what will be the k. So to find out m, I'll rearrange this equation, and m will be taking square on both sides. It will be t square divided by 4 pi square multiplied by k. T is the time period given 0.6 second, 0.6 square of this divided by 4 pi square, and k is mg by L. Now mg is 490 Newton and length is 20 centimeter. Converting it into meter, it will be 20 times 10 to the power minus 2 meters. That means 0.2, it will be 0.2 square of this. Yeah. Solving this expression, we'll get the mass. Let me calculate. So this will be 0.6 times 0.6 divided by 4. So 19 divided by 1, 2. So I'm getting 100. Okay, so the mass here that I'm getting, the value of mass here is 22.36 kg. I think wait. The value of k is mg by L, right? If it's that much, that is fine. Mg by L. Okay. So the mass of the body I get is 22.36 kg, and thus the weight of the body, we have been asked to calculate the weight of the body, that will be m times. I mean, this m was what? This was the maximum mass that can be kept for this, but we have been asked what is the weight of the body because of which this oscillation is happening. So using this maximum weight and maximum extension expression, we calculated the spring constant for this spring balance. Now using this, because it's a constant value, using this we are calculating the, okay, just to differentiate this was m maximum, okay, m bar I'm calling it, this was maximum displacement or something. So the mass that we want, we are calculating that the desired mass, required mass of this body was this, and for this was also the maximum m bar I'm writing, and from this we calculate it to be 22.36 multiplied by 9.8, it will give 219.13 kg meter per second square. That will be like approximately 219 Newton. So this will be the weight of the body in this case. So we know time period of oscillation is given by this expression. So first thing, we knew that to calculate mass of this body, we needed this value of spring constant, and to calculate the spring constant, we use the maximum weight that can be hanged in this spring balance and the maximum extension that can happen here. Using these two relations, we found out the spring constant value, and then we use the same thing here to find out the mass of this body. Okay. Okay. Now moving on to the next question. We have one more question. A spring having a spring constant 1200 Newton per meter is mounted on a horizontal table as shown in figure. Okay, this is this figure actually. Figure below. A mass of 3 kg. So this mass of 3 kg is attached. Spring constant we have already been given 1200 Newton per meter. Mass of 3 kg are attached to the free end of the spring. The mass is then pulled sideways to a distance of, so displacement here is 2 centimeter. Converting it into meter, it will be 0.02 meters, and released. So when it will be released, there will be some frequency. We need to calculate. It will oscillate above the equilibrium position, right? So we have been asked to calculate 3 things. First is frequency of oscillation. Frequency of oscillation will be 1 over time period, right? And since we know time period is given by 2 pi under root m by k, k is the spring constant, that means here the expression will be 1 over 2 pi under root k by m. Substituting these values, 1 over 2 pi, and k is 1200 divided by mass is 3 kg. This will be root of 400 will be, this will be 20, 10 over pi, 10 divided by 3.185. So it will be approximately 3.185 radian per second, or cycle per second you can call it. It's basically frequency, it's per second. Okay. Now next thing we need to calculate is maximum acceleration. And if you remember the expression that we had derived there, that when oscillation or simple harmonic motion is given by this equation, this is the amplitude, and sine omega t or cos omega t both are fine. Let's write sine omega t. In this case, when I will take double derivative here, acceleration will be minus omega square y. Okay, now using this expression and ignoring the negative sign, omega means under root. We know this, omega and the relation between k by m and omega, the angular frequency and spring constant, the relation is this. And also there is this one relation, acceleration depends on y in this fashion. That means omega square will be a by y. Using these two things, that means this is the equation. That means k by m is equal to a by y. This implies acceleration will be y times k by m. K is 1200, m is 3, x, the maximum x is 0.02. So acceleration will be, again this will be 400, and 400 times 0.02 is 8. So maximum acceleration will be this 8 meter per second square. Because we released it at that point, it will not, the displacement will not increase beyond that. So the displacement is maximum, means the acceleration is maximum at that point. So we have used the same value of displacement here, and thus this is the A max, maximum acceleration possible, which is 8 meter per second square. Now one more thing we need to calculate, that is maximum speed of the mass. Now maximum velocity of the mass, is given by this. If I solve this, like just to make it clear how we get this expression is, so y, if I take y is equal to a sine omega t, okay, and this is dy by dt, I mean velocity is first derivative, so this will be a omega cos omega t, right? Now at mean, okay, if I put it into this form, a omega, and we know cos square theta plus sine square theta is 1. We know this identity, right? Using the same thing here, I mean cos square theta will be 1 minus sine square theta. So this thing, substituting here, cos in terms of sine will be 1 minus sine square omega t, and root of this is the velocity. Now sine omega t from here, if you see from here, what will be the value of sine omega t? Sine omega t will be y by a. Putting that here, what is this? This is capital A. Amplitude this is. Oh, okay. 1 minus sine, okay, this is y square by a square. So we know at mean position, displacement is 0, right? Displacement is 0 means velocity is a omega, and we know that at mean position the velocity is maximum. The velocity becomes 0 at extreme position. At extreme position velocity becomes 0, and at mean position velocity is maximum, and mean position displacement is 0, so velocity is in this form, a times omega. A is the amplitude, omega is the angular frequency. So here we have been asked to calculate maximum speed of the mass, means maximum velocity. So from this that we derive, we can directly use the formula a times omega. So the amplitude the maximum displacement will be, we had calculated maximum displacement expression. This thing. The maximum displacement is actually given 0.02 meter, okay, and the maximum displacement is given 0.02, and omega we know it's root of k by m. So this will be, again, k is 1200, m is 3 kg, so this will be 400. So this will be 20, and this will be 0.4 meters per second. So this will be the V max. So this question is done. Okay, we have one more question. Correct, class is pretty long. A circular disc of mass 10 kg is suspended by a wire attached to its center. So a circular disc is attached with a wire like this. With its center it's attached. The wire is twisted. Okay, the wire is twisted by rotating the disc, and then it's released. So it will start rotating about this spring. The period of torsional oscillation, this is called actually torsional oscillation. That's why that Paul wheel or Paul pendulum, we were calling it torsional pendulum. So this motion, this kind of pendulum is called torsional pendulum, and oscillation is called torsional oscillation. And the time period is found to be 1.5 seconds. The radius of the disc is 15 centimeter. And determine the torsional spring constant of the wire. And we have also been given that torsional spring constant alpha is defined by the relation J is equal to minus alpha theta, where J is the restoring couple and theta is the angle of twist. Okay, so we have been given that J is restoring couple and the value is denoted by this, where theta is the angle of twist. Like in oscillation we say about angle of displacement, here it is the angle of twist. And alpha is the spring constant that we have been asked to calculate, right? Yeah, we have been asked to calculate alpha. Okay, so what we'll do is, we know we have been given time period. Again, let's write first. Okay, I'll convert it into meter. Centimeter means 0.15 meters. We have also been given time period, which is 1.5 seconds. Radius is this. Mass of the body is 10 kg. Okay, now from time period we know time period for a body, actually for oscillations we write it, I mean for simple harmonic motion, we write it as mass, I mean 2 pi under root m by k, right? Yeah, but basically what I mean this m by k or these things may vary for different kind of body doing simple harmonic motion. Like what it basically means, time period is actually the ratio of inertia of the body and the spring factor of the body or spring constant of the body. Okay, basically it's this. So in kind of simple harmonic motion, be it the spring mass system or oscillation, we have this m by k. Okay, I mean the inertia is because of the mass and spring constant is k. But for this torsional pendulum, this inertia will be because it's rotational motion here. So we know the rotational analog of mass is moment of inertia. So here this inertia will be due to the moment of inertia, which we had discussed in earlier sessions. This inertia is due to moment of inertia, and the spring constant is the, here we have been given the spring constant is alpha. This is torsional spring constant actually. So we need to find out this I, T we already know, then we will be able to find out this torsional spring constant. So because it's a circular disc and we know how to calculate, I mean we already know moment of inertia for circular disc is given by half mass of the body and radius, square of the radius. So mass is 10 kg, radius is 0.15 meters. Taking square of this, moment of inertia will be 0.15 times. I am calculating in my calculator. So value is 0.1125. This is what I am getting. Moment of inertia value is 0.1125 kg meter square. Putting that here, or first let me rearrange this. Alpha will be T over 2 pi, no wait, this will be like this. 1 over alpha will be T over 2 pi and 1 over I. This will be in square. Again rearranging, it will be, alpha will be 4 pi square divided by T square times this moment of inertia expression. And putting the values, 4 pi square, moment of inertia is 0.1125 divided by time period, which is 1.5 seconds, square of that. Final value we'll get is 4 times 3.4 times 0.125 divided by 1.972. So I'm getting 1.972 Newton meter per radian. So this will be the torsional spring constant value of this wire. This is the answer. Okay, so these were the questions based on the simple harmonic motion. Now next week there will be lectures on compound pendulum and the corresponding experiment. So here I'll just introduce a quick introduction. What is difference between simple pendulum and compound pendulum? So in simple pendulum, we know we have, where is my pen? Okay, yeah. So simple pendulum is suspended by support and by a massless string, and the bob has all the mass. This is the case of simple pendulum. Whereas a compound pendulum is a kind of body where the mass of the body is extended throughout. I mean, it's something like this rod. Instead of having this massless spring and all the mass at the end, in compound pendulum is a pendulum which, okay, it's it has some pivot kind of thing, and say a rod is fixed at a rod is set here, and this rod is oscillating now about the fixed mean position. It's doing to and fro motion, but here the mass is not at the end. Mass is not at the end, it's throughout. It's throughout this whole where it's not at the end but throughout this shape, throughout this body. So how it's defined is a rigid body which can swing in a vertical plane about some axis passing through it is called a compound pendulum. A compound pendulum consists of extended mass. So in simple pendulum, all the mass was at one particular end. This was simple pendulum, right? This was simple pendulum. All the mass was at one end. Whereas in compound pendulum, the mass is extended and it oscillates freely around the horizontal axis, but the mass is extended here. It could be any kind of body. It doesn't need to be a rod only, but just I have introduced this, and we'll talk about it later in next week's interactive session. And this is the end today. Okay, thank you.